Today we are going to discuss crystal field theory and the formation of tetrahedral compound. Put the heading crystal field theory, that is CFT. Okay, see. So in CFT we will discuss particularly the formation of tetrahedral compound. Complex, tetrahedral complex, coordination complex. Okay, see, we know that this crystal field theory has some assumptions like here the metal considered as positively charged or stationary charge, and this ligands considered as negatively charged, that is moving charge. So between these two metals and ligand, electrostatic force of attraction works. Electrostatic force of attractions. Okay, now see, in the formation of a tetrahedral complex, that a metal present in the tetrahedral void that is created by four ligands. Okay, now see, suppose this is a cube. Okay, this is the cube that I'm going to draw. Okay, see, I'm drawing this cube here now. This is okay. I want to explain this in 3D. That's why I'm drawing this cube. See, this is the cube. Here we know the tetrahedral molecules look like two bonds will be in plane and two bonds will be in perpendicular to this plane. That is tetrahedral molecule, right? Okay. So see here, in this cube, in this cube, hmm, this is your metal. Okay, that is present in tetrahedral void that created by these ligands, four ligands. Okay, how see, these all are ligands. Okay, so here this is the your tetrahedral void where metal present. Okay, okay, so see, and we also know that we have to keep in mind one thing here in this formation of tetrahedral complex, that initially here all the ligands actually they approach from the corner, they approach from the corner, like say here from this corner, with all ligands from this corner, from this corner, and from this corner. That means four ligands approach from from we can say four ligands are approached from corner of the cube. Okay, see now, actually due to these ligands, okay, here two field two field uh, uh, two field are arises. Okay, one is that is near field, or we can say one is far field, another one is near field. Okay, let me explain what is this far field and near field. See here, so this is um, the axis. Okay, it is x y, and this is your dx square minus dy square orbital of this metal, d block metals, and this is dxy dxy orbitals. This is what dxy orbital that is present in between the axis, that is in if you represent in cube, that will be in corner side. So what I am saying here, that dxy dyz and dzx, these three orbital, uh, they are present in between the axis, and that is non-axial or along the axis, non-axial orbitals. These non-axial orbitals present in between the axis. So here in tetrahedral ligand approaching from this corner. So see what happens here in the far field. I'm explaining first far field. What is this far field here? Okay, see. So in far field, ligand is approaching from this infinite distance. Okay, this is ligand at infinite distance. Okay, so here metal is there. Okay, now see, due to these ligands, what happened, all the metals, when this ligand at infinite distance, all the orbitals, like that dx square minus y square and d, like five orbitals, dx square minus y square dz square dxy dyz dzx, all the orbitals will face same type of repulsion, or same type of attractions, you can say that way. Okay, same type of repulsion. Okay, because of metal positive charge z effective, there is a attraction between this metal and this ligands. So ligand is coming nearer towards this metal. Okay, so here these orbitals, like non-axial and axial orbital, axial and non-axial orbitals uh, face same repulsion in far field, when ligand that is present at infinite distance. Okay, but when this ligand approaches, when this ligand approaches um, when this ligand is nearer to this, because this ligand is coming, right, when this ligand is nearer to this tetrahedral geometry, then here this ligand, there will be a direct head-on repulsion between this non-axial orbital and these ligands, and there will be less repulsion between these what axial orbital, that is dx square minus y square and dz square orbital, and these ligands. Okay, that's why splitting happens in this. Okay, so I can tell you one thing. See here, now I'm drawing this splitting diagram. See, this is your 5 orbital dxy dyz dzx and dx square minus y square and dz square. Okay, this is present in ground state. Okay, now see, due to far field, because metal, due to z effective, ligand is coming nearer to this metal, that's why this all, and also they are having same type of repulsion. That means all axial and non-axial orbital, this is the same type of repulsion. That's why their energy increasing in a similar way. That means in excited state also they are having uh, all orbitals are degenerate orbitals. Okay. Now due to this is far field. Okay. Now in a near field, what happens? In near field, there is the hidden repulsion between these non-axial orbitals and these ligands. That's why here three non-axial orbitals are there. These are the three non-axial orbitals, and these two are axial orbitals. So these three non-axial orbitals, their energy will increase. Their energy will increase, and here these two orbitals, axial orbitals, their energy will decrease. Okay, here this is known as splitting diagram of tetrahedral, right? Tetrahedral complex. Now see, and this two energy is known as E, and this three energy is known as T2. Okay, I'm writing here this thing, this is dxy, dyz, and dzx. This is dx square minus y square, and this is dz square. Okay, and we also know that this center is known as what? Berry center. It is what? Berry center energy. Okay, now this gap, this energy gap, okay, that is known as delta t, del t, because that is for tetrahedral splitting. Okay, now say this energy that is increased by 0.4, okay, two part 0.4 delta t, and this energy that is decreased by minus 0.6 delta t. Okay, this is the splitting of tetrahedral complex. Okay, so here I'm repeating again. See, this is the ground state orbital, that five orbitals of this metal present. Okay, when ligands approaching from this like infinite distance, okay, then due to due to same type of repulsion and attraction filled by these five orbitals, they all are excited with with degenerate energy level, with all orbitals having same energy. Now in near field, because of non-axial orbitals feeling high repulsion due to the approaching of ligand through corner. Okay, that's why these three orbitals getting higher energy level, and these two orbital getting low energy level. That is the thing. It is the splitting in tetrahedral complex. That's it.